Good afternoon, everyone. My name is Jason Bavington. I'm the Director of Illusions, and for your time today, I'll be presenting on realizing ShiraX, an open source platform that creates turnkey AI-based educational apps for autonomous learning. I need to know your toes for this one. We got like 100 slides to go. So first, just a little bit quick background about our company. We're a digital media company. We've been designing solutions for a number of organizations for many, many years. Next slide. We're based near Toronto, Ontario. We're actually in a town called Guelph, but no one's ever heard of it. So we always just say we're just 1 hour west of Toronto. And we've been crafting digital solutions for over 2 decades. We started our first website back in 1994. For those of you programmers in the room, we used Windows Notepad, best coding platform at the time. We moved into social media in 2008 by creating a Facebook page for an organization. Facebook pages were revolutionary at the time, and we're able to bring that forward to our client. And we developed our first mobile app in 2012. It's actually still the top performing app in its niche today on Apple. We've received curated invitations from Apple, which we're very proud of. But just before I continue, I just wanted to do a recap of the global education situation. As many of you know, there are over 250 million children around the world who can't read, they can't write, and they can't do math. That's 250 million people who don't have basic access to this educational knowledge that is required. As we know, many of these people live in impoverished areas, and for this reason, they have no access to schools or teachers. Now, if schools were available, it would require 1.5 million teachers to address this issue. But as we know, there's simply no way to meet that need given the current approaches that we have. The infrastructure simply is not there, and even if the schools were there and there was electricity and books, there's no teachers to fill those schools. So it's a significant issue that we're faced against. Our solution to this situation is digital in nature, and it's known as ShiraX, which is an AI-based teaching system. The system is based on website interaction by the educator. The educator can be a layperson, they don't require technical knowledge, and they can create an application solution for children. The application solution is self-teaching in nature, and it's personally engaging in nature. And the educational app can be exported by the system to phones, tablets, computers, or a standalone website. Now, at the core of our system, as it relates to the children, is artificial intelligence. Now, we offer artificial intelligence at a variety of levels. The AI can interact with the child, the AI can interact with the environment, and the AI can interact with the children's friends. So the way that works is if a child had a tablet and they're using our system, the tablet would say through speech, "Hey, show me what's happening around you today." And the child might respond by saying, "Oh, there's my dad fixing the door," or "There's a goat," or "There's a bird flying past," or "There's a tree." And what the system will do through speech-to-text analysis is it will pull out the keywords that it's familiar with from its database, and that's where the learning opportunity begins. So the system might respond by saying, "Oh, you mentioned the word goat. Let's start learning about the word goat today." Goat is spelled G-O-A-T, and the learning continues that way. The system can also interact with the child's environment through image recognition. So if the child's holding on a tablet, telling the system what's happening around them, the system could pick up a chair or a table through its recognition and say, "Oh, I see you're in a room with a table or a chair. Let's learn about chair today. Let's read it with a key article about a chair, about birds flying past." So the system can interact with the environment to provide great context-relevant education. Once a child masters a concept, say they learn how to spell the word goat, or they learn how to add 2 numbers together, once they've done that successfully through testing, the system will say, "Oh, you've learned how to spell the word goat. Now go show your friend how to spell the word goat." And now we're encouraging peer-to-peer interaction, which we know can be very successful in groups of 4 or less. So I can go to my friend and teach them the word goat, and my friend can come back to me and teach me about the word sand, because they're having a completely different educational experience. Now, ShiraX was originally developed as part of the Global Learning Xprize Challenge. Xprize is an organization out of California, and they're responsible for creating these grand challenges to push various industries or spaces forward in a positive way. Now, the Global Learning Xprize Challenge on their website reads that the challenge is designed to challenge teams to create tablet-based scalable software that will enable children in developing countries to teach themselves reading, writing, and math in 15 months or less. So it's a massive challenge. They like to call it audacious challenges, but this is the challenge they set forth to the world to solve. Now our team was a team of 25 people, and we collectively worked thousands of hours over the course of development of a year. We have programmers, educators, designers, illustrators, linguists, and we all worked for $0 an hour. So we had no funding for this system, but we were driven by our passion and the cause, and just wanting to make a positive impact on the world. Out of 198 Xprize teams that were around the world, ShiraX placed in the top 20 cohort in the competition. So we were very proud of this accomplishment, especially considering our significant lack in financial resources. Now here's an example of the ShiraX system in action. This is one of the educators working with the system to create an app. The interface is designed to be very user-friendly, very efficient, and we just want the educator to simply be able to make the app. So in this case, they're working on animals, lions today. So the educator can drag in a picture of a lion, they create a button on the screen, and then here, this is called an action button. Next slide, please. And when you click that button, you can apply any kind of action to buttons or other elements on the screen. So they might want the user to navigate to another screen, they might want to play a sound, in this case the sound of a lion roaring. You might want to display board images of lions. You might want to run a story. We have open source storybooks from storyweaver.org that are included as part of the platform. I also want to mention that our entire platform is open source in nature. We can have a scratch pad so the child can practice writing, practice calculations. We have a variety of languages built in with built-in characters and words and sentences that the educator can drag in. We also, people love taking selfies, as we know. We want the kids to take selfies using the front of your camera. We want them to interact with the device with as much as possible, because the more they interact with the device, the more they're going to learn as a result. We can record the child's voice for playback later. It's useful for pronunciation. And then we have a variety of text-to-speech or speech-to-text features that encourage further interactivity with the child. One of our favorite features is we are able to offer Wikipedia in offline mode or no internet. And in the future, we'd also like to be able to add games, so an educator can simply, with one click, add the entirety of Wikipedia to the app, and later be able to add games. Currently, we have Wikipedia in 48 languages in offline mode. And as I mentioned, we have several hundred storybooks that are also open source at a variety of reading levels. And the system is also able to recognize handwriting in 105 languages. This is useful when you're trying to teach a child how to write the letter G or write the word Go. The system can interpret the handwriting to determine the success of learning the letter or word. The project can export to Android, iOS, the web, or Raspberry Pi, and we're looking at additional platforms in the future as they become available and popularized. Now, we believe this system represents a very unique approach to address the educational gap we mentioned with over 250 million children that don't have access to school using traditional means. As the system is based on autonomous learning, it's child-directed, context-directed, and as opposed to a typical learning structure that's linear in fashion, we built in a learning structure that's more cyclical and story-based approach, because we know this works well in continents like Africa, where the culture tends to think in a more cyclical, story-based fashion as opposed to the Western world, which thinks in a more linear fashion. So we designed the platform to be accessible to as many people as possible, everyone from educators and solos, right up to large organizations and corporations that are working on educational solutions. We wanted to make sure that anyone can use the system to design any kind of educational app and deploy it to any platform. Currently, the coding of our project is on hold as we explore funding opportunities. We're also working with partners to further the reach of our program. And we're also working on expanding the technical base to be able to offer additional technical solutions and features inside the system. Now, we are part of a UNESCO Chairs program known as Gfdl, or Global Smart Disruptive Learning. The chair is based in Quebec, Canada. We have the head of the chair, Mr. Richard here today. Next slide, please. And the goal of our research chair is to meet the UNESCO Sustainability Development Goal number 4 of quality education. And it's the intention of our research chair to do this through an application-based solution. These are a sample of some of our partners that we're working with as part of the UNESCO chair. We have partners in the south, in Senegal, Burkina Faso, Algeria, and in the north we have partners in France and the that's located in Canada. The university in Montreal, Quebec that we're working with, which ShiraX is from, is Taylor University, and they have a research center known as the Research Center. That's the administrative coordination of the research chair. So So just finally a breakdown of the GSDL acronym. G is for global. We want to make sure that the research share solution is applicable to countries all around the world. S is for smart. As I mentioned, we're really focusing on an artificial intelligence-based approach to learning, which we feel can really leapfrog those success models in education. We're trying to de-disrupt in a positive way. We're trying to break free from traditional ways of educating and traditional pedagogies and moving into a new style of learning that is disruptive yet positive. And finally, we want to make sure learning is accessible to as many people and generations and demographics as possible. The goals of the GSDL program are to create a phone or tablet-based solution because this is what we feel are the best platforms to reach the most number of kids because they're highly affordable. Number two, ensure the system is self-learning and child-directed, again, for the reasons I mentioned and the benefits that we believe are achieved using this model. And finally, to make sure the system meets the needs of not only children, but also youth, young adults, and adults. So again, because the system can handle any kind of content, why not produce any kind of content from little kids right up to the adults? So finally, the next step that we're pursuing to help realize the system is we are trying to pursue funding, see how we can bring some money into this to achieve our coding objectives. We will continue with the UNESCO Chairs program. It's a 4-year program, which we're extremely excited about. A lot can happen in 4 years. It's going to be amazing to see where this program goes. And finally, working on the technical aspects of the program, which include natural language processing, working on deep neural networks, which is deep speak for a system can recognize a tree because it can see a tree. So the deep neural network works with the image recognition to make sure that the system can pick up objects from the environment to help teach a child. And finally, non-symbolic artificial intelligence. This is where the real artificial intelligence, in our opinion, comes into play, because instead of having just a lot of smart math behind the scenes where the system connects the dots, the system itself starts to code its own programming, and it starts to create its own logic based on the user feedback and the environmental feedback, and this is where the AI really starts to shine. So we're really excited to see where this goes in the next 3 years. It's amazing, and we're really, really thrilled to be able to present this to you. Thank you very much. Again, my name is Jason Bavington.
Thanks very much. Yeah, we would also have time for 1 or 2 brief questions or comments. Otherwise, we're going to yes, please.
I have a quick question. So you're one of the first AI systems that's mentioned it's interactive with the environment instead of just being on the computer. So do you think there's potential kind of like security issues with this or like data protection issues? So is this like a two-way mechanism? So let's say like what if someone brings it into their home and instead of showing a goat, you know, it's like their father's hitting the mother, or like it's showing abuse or something like that, you know, how does that go into?
So, well, 2 things. One thing is our system is designed to be used offline. So in terms of like analytics or someone watching behind the scenes, that doesn't come into play. Second, in the context that you described, if the system was able to recognize those kinds of images, it would have to have it in a database. That's what we're talking about, symbolic AI. It would have to match what it sees to what's in its database. So again, because our system can be used by anyone, if there was an educator or an organization that wanted to try and address those issues, they could of course code that into the system and say, you know, if there are signs of abuse, we have to figure out what that looks like to make the system recognize it. And yeah, maybe the system could send out a call for help if it is internet enabled, or maybe it could educate the child. And again, it gets tricky because you're dealing with cultures and values. But hey, this isn't right. Maybe there's some options for you to help address this situation.
But do you know where like the legality is in that?
I think it'd be very context specific and case specific. It'd be based on the kind of app that's being created and then what the purpose is for that. Again, because our system is kind of open-ended, it's like WordPress. For those of you familiar with WordPress, WordPress creates websites, but WordPress is just a tool. It's how we use that tool. All of our cell phones, they can be used for good or bad. It's not necessarily the cell phone's fault. If it's used for good or bad, it's simply a cell phone. So it's a tool, and then we just have to use that tool in certain ways to accomplish objectives, which of course is more positive. But I do recognize your point that there are larger issues and legalities and institutional items that do come into play as these apps are developed for different purposes that they're developed for.
Okay, I think we'll...
Thank you.
But you said everything's offline, so how are you managing that processing power and the data Are you saying that, are you developing your own devices, or are you basically using the user's end devices?
The intention is to use the end devices. So as I mentioned, it works on Android, or iOS, or Raspberry Pi. The system itself has a very low overhead. It doesn't require a lot of computational cycles. So if you have like a half-decent tablet, like with Xprize, we were working on a tablet. We received the tablets in 2016, and it's totally fine now. It's 2019, and the technology keeps advancing, right? So, you know, a basic system with a couple processors, 64 gigs of memory, is more than enough to handle what it can do. As we develop more of the neural network and kind of non-symbolic artificial intelligence, it would require a higher processing power. But by the time we get to that point, the processor will be commonplace. Just like a Raspberry Pi is so much more powerful than a computer like 5, 6, 7 years ago. So yeah, we're confident that hardware can get there.
Okay, thanks very much. Thank you.